Hello, I am Rafael, and I'm going to give a short overview over my PhD, which is entitled Damage Redirection and Self-Healing in Skin-Stiffened Structures. I'm working under the supervision of Ian Bond and Richard Trask. Here's a short outline of my presentation. I'm going to start with a short introduction in the thematic about skin-stiffened structures and self-healing, and then I'm going to present the three different redirection mechanisms which I'm using. So, skin-stiffened structures are widely used due to their efficiency in order to carry loads, and the material which they are used nowadays is composite materials because of their high specific mechanical properties. I want to introduce a self-healing capability to this type of structures, but in order to do so, I can't use directly a 2D loading scenario, but I have to use a simplified specimen type, and I've selected the skin-stiffened bond specimens, which basically mimic the stress diet which happens at the tip of a flange. Basically, true thickness stresses arise, which can lead to delaminations and debonding of this stringer, which can lead to failure of the structure. In order to overcome this nowadays, safety margins are used with induced weight penalties, and periodic inspections are scheduled, and in case that the damage is detected, repair is done. The first two systems, the intrinsic and the capsule-based, have the ability to be an autonomous system. However, they are only suitable for small damage volumes, and more important, they are incorporated into the structure itself during manufacturing. So the healing agent inside has to survive the curing cycle of the material, and also as it is part of the structure, it has to be assured that the self-healing resin or the film has the ability to be active as long as the structure is in use. The last, the vascular-based self-healing, is also suitable for an autonomous system. And more interestingly, as the crack plane is flooded by an injection of the healing resin, it is suitable for larger damage volumes. As we have an embedded vascular network into the structure, we can use this for monitoring the health status of the structure. And as the healing agent isn't embedded in the structure during manufacturing, we don't have to survive the manufacturing process. However, one of the largest challenges in order to use a vascular network for healing is that we have to embed the vasculature into the structure and also to assure the connectivity between the damage and the healing feature. So if you want to apply self-healing to a structural feature, you have to manage both the structural feature itself and also the self-healing feature. So you have to choose your self-healing capability to your size. For example, if you have a large damage size, perhaps you have to use a foaming healing agent, but also, more important, you have to change the philosophy of design. So you have to start tolerating the damage in your structure and manage where the damage goes in. And this is what I'm working currently in my research in redirecting the damage. So I'm working at the moment with three different redirection mechanisms, which are interleaves, vascles, and the ply structure itself. And I introduced them in skin-stiffened bond specimen, which I tested both in static and fatigue conditions. So let's start with the first redirection mechanism. The first one consists in a selective interleaving, which means that I introduce a thermoplastic film at different ply interfaces, and this interface, this selective interleaves, arrest locally the laminations. However, interestingly, in the skin-stiffened bond specimen, the delaminations can propagate in two different modes. They can propagate along one ply interface, but also they can migrate into lower interfaces. So what we have found is that these interleaves arrest the delaminations, and afterwards the delaminations tend to migrate into lower interfaces. And in this way, as we can see in this time-lapse video, we are able to propagate the delamination from the damaged side into the vascular network where we have injected in this time-lapse red dye penetrant, and we see that there's connectivity between the damage and the vascular network. The second redirection mechanism that I've used are the vascles itself, because the transfer vascles create in front of the delamination like a stress-free state and arrest the delamination. And then afterwards, according to the resolved tensile stresses, the delamination might, or you can control according to the resolved tensile stresses, along which interface the delamination will propagate afterwards. So As you can see in this micrograph of the skin-stiffened bond specimen, the propagating delamination has encountered a transverse vascule, and afterwards it jumps into a lower ply interface. More interestingly, by the first two mechanisms that I presented, the interleaves and the vascules, as we do only small changes to the overall structure of the component, we haven't found any large difference between the global mechanical properties. And also in this case, I want to highlight a first trial of initial healing result, where we have here in this slide the stiffness decay as function of cycles, and here we have the pristine specimens which we cycled to 40,000 cycles, and with some specimens we cycled only to 20,000 cycles when we injected a low viscosity healing agent, cured the specimen and cycled it again, and we recovered a certain amount of the stiffness. The last mechanism which I've studied is the ply structure itself, because if you have a delamination, it tends to propagate along the ply interface where ply is oriented in the direction of propagation. So if you have, for example, this DCB specimen here, and we have some scarf plies which go out of the midplane, so in this way, when the delamination encounters this interface, the delamination will migrate out of the midplane, and we can arrest the delamination and steer it into predefined areas. As we can see also in this micrograph here of a skin-stiffened bond specimen, where we have combined a scarf ply with some interleaves in order to redirect the delamination from the center of the specimens into the bond line, where we think that from a manufacturing point of view, it will be easier to introduce vascules. Okay, now I'm going to sum up my results. So from a global perspective, the interleaves and vascules themselves, by introducing them into the structure, we don't change the global mechanical performance. With the three control mechanisms, we are able to redirect the damage into the interfaces which are for our interest. And this could be used for both for damage visualization or structural health monitoring, but also for healing. And we also have some initial healing results, and we are currently working in a tougher resin, which low viscosity toughened resin. If you want to have further information, you can visit our website, the Access Multifunctional one. I want to thank both EPSRC and Obra Social La Caixa for funding. Thank you very much for your attention.